All right. So, we are going to learn another method for rotating volumes of revolution. Why? Let me give you an example. Here I have this figure right here. I have a parabola and a line intersecting. If I asked you to rotate that about the y-axis, and we only know the disc washer method, first of all, what kind of rectangles do we need to draw in? DY, okay. Horizontal, right? Now, what becomes the issue with using these horizontal rectangles to write our integral? We would have to break it up into two integrals, wouldn't we? Because the function on the right is the same, but the function on the left changes right there. Okay? If we could do this in one integral, would it be better? Would it be less work? It would be, okay? So today we are going to learn the shell method, which will give us an opportunity to do a problem like that with only one integral instead of two. Okay? Calling this the shell method, and I'll show you why it's called the shell method. But do you remember how I talked to you about the disc washer method, and then our rectangles needed to be perpendicular to the axis of rotation, so I called it the perpendicular method? Do you remember that cheesy little saying? Okay, here's where it's really going to come in handy. For the shell method, we are going to want parallel rectangles that we rotate around. And so parashell is my cheesy way for you to remember what kind of rectangles that you need. Okay? Am I going to force you to use those words? No. But if it's helpful, they are there for you.
It's almost as bad as BB.
I didn't even make that up. Okay. So, do you recognize this? That's the pictures I drew on the very first slide, right? Okay, so instead of breaking those up into horizontal bars, I'm going to break them up with vertical rectangles and rotate them around. If I rotate that around the y-axis, can you see how it makes a cylinder shape? Okay, this is what we call a shell. Okay, shell like a cylinder. Okay, I'll let you watch it again. So we're going to break it up into parallel rectangles and rotate it around so it makes a shell. Now, here I have a shell, and I'm going to unwrap it. Okay, let's talk about the dimensions of this rectangle that I just unfolded. Okay, this is just the height, right? We have a thickness, but how long is this rectangle? If it's circular and then I cut it and I lay it out flat, how do we know how long it is?
It's the circumference area.
Okay, it's the circumference of whatever that circle is. Do you agree? Okay, so this rectangle, we have circumference as our length, and then of course we have the height and the width. Okay, how do we find circumference? 2 pi r. So if I want the volume of this shell, I could take the height times the width times the circumference, which is 2 pi r. Right? Well, what we have to do is we have to add up all of these shells together. What do we do in calculus that adds up a bunch of infinitely small pieces? Say it louder.
Integrate.
We integrate, okay? So we're going to have to integrate to add up all of these shells together, okay? So let's talk about where we get the radius of our shell, where do we get the height of our shell, and what's the thickness. Now, we can answer that first. The width is like our thickness. What is that going to be? dy or dx, depending on what we're doing. Do you agree? Okay. I'm going to come back to this picture here. Okay, I know there's a lot going on right now. All right, but we have a piece of our curve that we've rotated around, and there is a shell. There's our cylinder. Okay, so the height of the cylinder is just going to be top function minus bottom function, just like we would with area. Okay, so that is going to represent our height. Then each of these, I'm going to come back to this figure right here. Each of these rectangles have vary in length away from the axis of rotation, right? If we're rotating around the y-axis, then all of these would be x away. Because they're all different, so we can't say that it's like 2 or 3 or 4. But they're all, this distance from any point here to the y-axis, that's a horizontal distance, so we call that x, right? A horizontal distance away from the y-axis is x. So, when we come over here, our radius, we're going to call x. Go ahead and write this down, labeling those. And then you can see this figure, this figure over here is taking those shells and wrapping them around so you can visually see what those shells look like all together. Isn't that a cool animation? Watch it. So you can really see the difference between these shells and the washers. This one is. Do you see how they're like cylindrical shells? Whereas last week we were working with those really, really thin discs and washers. Okay. So visualizing that rectangle rotating around your axis is going to be important, especially when we come to Friday, because you're going to have to recognize, is this rectangle going to make a shell, or is this rectangle going to make a disc? So, we're going to try a few examples. Are you ready? Okay, so we're going to do this one. Y equals 1/2 x, y equals x minus 1 squared, and we're going to rotate it about the y-axis. So we get this shape here. So I'm going to go ahead and I'm going to delete this graphic so we have room to work. Okay, y equals x minus 1 squared. You've already seen the graph, but you should recognize that that is just a parabola shifted. What? And then we have y equals 1/2 x that intersects it. We are going to rotate about the y-axis. If we are going to use the shell method, we need parallel rectangles to rotate about that axis of rotation. So they have thickness dx. That is telling us we need to integrate with respect to x. So we need these intersection points right here. How would you like to determine those?
I'd say we FOIL and then we solve.
Are you saying you want x minus 1 squared to be equal to 1/2 x and you want to solve that? Okay. Okay. So we have x squared minus 5/2 x plus 1 equals 0. Okay. Do we really want to try to factor that?
Yes.
It can just be -2 and -1/2.
Like that? Does that work?
Yes.
If you don't want to have to think about fractions, you know it is possible to multiply both sides by 2, and then you would have a trinomial without fractions that you could try to factor. You get the same answer. So when we go to set up our integral, we would have limits of integration of 1/2 to 2. Now, since we are using the shell method, we're going to have 2 pi here times the radius times the height times the thickness. Okay. Now the radius. Any rectangle that I would draw in this figure, how far away would it be from the axis of rotation? How far are each of these from the axis of rotation? They are all x away. That is our radius. Then we need the height of each of these rectangles. So all we have to do is top minus bottom. Our top function is our line, minus the bottom function is the parabola. What makes the shell method nice is it's not squaring anything. So sometimes it's easier to distribute and do by hand. Okay. Go ahead and since this probably is not one I would make you do by hand since it does have a little bit of algebra inside of it, go ahead and punch this into your calculator for me. You have something for me? So here again, I would do this in your calculator. See if it's a fraction or not. If it's a fraction, then multiply it by 2 pi. If it's not a fraction, multiply it by 2 pi for a decimal. Okay? I'm guessing this one's going to be able to be a fraction. What do you have?
I have 45 pi over 32.
And that's after you multiply by the 2 pi?
Yeah.
Okay, Logan has 45 pi over 32. Do you agree? Yeah? Okay, so sorry I didn't say it right away, but put this in either without the pi or without the 2 pi, and then multiply it by it afterwards. Yes?
Like, I understand the process and everything, but if this exact function were to rotate around the x-axis, then couldn't you just use the dishwasher method?
That is an excellent question. Yes, if we wanted to go around the x-axis, then it would be best to use the dishwasher method so that we wouldn't have to, since the right and left, since the function on the left changes, right? So if we went around the x-axis, then yes, we would use the dishwasher method. Okay? So, you know, this does give you an opportunity, no matter what we rotate about, because if we would want to use the dishwasher method for this, we would have to integrate with respect to y. But the shell method, we integrate with respect to x. So we do have the capabilities, if it's possible, to integrate with respect to x every single time. Now, that's not always convenient, and that's not always the best option, but this gives us that opportunity. But do you see we're visualizing what shape that rectangle is making as it rotates around is important? So we can determine, are we making shells, are we making washers, or discs? All right, next set of information. Next example, whatever. What's making you nervous there?
Sign.
You know how to graph the sign, don't you?
I forget if you start in the middle or you start on the bottom or you start on the top.
Well,
It's either the middle or the top. I think it's the middle. No.
what's the sign of 0?
We go cosine sign or is it cosine? Wait, no, sign.
Alphabetical order.
0.
Okay.
Yes, I was right.
So this is the graph of sine. But if we're bounded by y equals 0, x equals 0, and this would be x equals pi, we can erase that over there. So what we're going to do is we're going to rotate this about the y-axis, and it's going to kind of make a bundt cake, right, without the hole when it rotates around. Now, I'm really sad because with our ice day and snow day, we don't have time to do a lab where we use volumes of revolution to measure the volume of a bundt cake.
What's a bundt cake?
You know what a bundt cake is?
No. Oh, I know what
It's like a
cake is.
circular cake. With like a whole, it's like, I'm gonna have to, huh? Like an angel food cake is like a bundt cake, except the bundt cake is round instead of like squarish.
Is that the one you hide like the baby in and you're supposed to cut into it and cover? Not the baby.
No. I will show you a picture of a bundt cake when we are finished with our lesson. Okay? But typically we get to use these volumes of revolution in a lab that involves cake, but because of our snow days we don't get to do that. Like I make cake and bring it in and everything. We should still get the cake.
Logan.
I'll think about it.
Yeah,
Not like an actual.
and then like whoever gets the little baby, like
Yeah,
good luck.
good luck for a year.
I understand what you were saying.
Oh, yeah.
Okay,
Real baby.
so here is where the shell method is nice. We have no way to rotate horizontal rectangles because we can't rewrite y equals the sine of x. We can't. I mean, not in a way to do a right minus left. All right? So what we have to do is we have to use No. We have to use parallel rectangles to our y-axis that have thickness dy. Everyone stare at that rectangle and imagine it rotating around, creating a shell, a cylindrical shell. Okay? So since this is the shell method, we have 2 pi times radius times height times thickness. Our radius, how far away from the axis of rotation will each of those rectangles be? X away. Times, how tall are each of these rectangles? So what's our top function? Sine. What's our bottom function?
0.
So each of these are just sine of x minus 0 in height. And then they've already told us that our region stretches from 0 to pi. Until you get to calculus 2, you do not have the tools to integrate this by hand, so you must put it in your calculator.
Well, could you write it as pi squared? Or do you just want to, because it gives you pi and make it look like 2 pi?
I mean, I guess if you put that I wouldn't like have it wrong.
Yeah.
But I'd more be looking for a decimal. So Logan noticed that when he put this in, he got pi, like 3.14, blah, 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 blah. And so he asked, could you write 2 pi squared? You could, but let's just make it a decimal. All right? And so what do you get as a decimal?
19.74.
All right. What do you think so far? It's nice to have a second option, isn't it? Okay, I've always given you really nice problems to do with the dishwasher method, but now it doesn't matter what kind of problem I throw at you, you can use either one. Yes?
Is that outside one always gonna be X?
Until we rotate about a different axis of rotation.
So tomorrow?
Well, and kind of today. We have one more example.
Not too bad.
What?
Nothing wrong.
Why is this example different?
Because it's Y.
We're rotating about the x-axis now. So y equals x squared is a parabola. 4x is a line. They intersect like that. Do you agree?
Yes.
We are going to rotate around the x-axis. Now, I know that we can do this with the dishwasher method just fine. But let's see what it looks like with the shell method. Okay, because that is what you're going to practice in your homework, is the shell method. So if we're going to use the shell method, we need parallel, pair is shell, rectangles. So they're going to have thickness dy. What are our points of intersection in terms of y?
0, 4.
And
0, 16.
0, 16? Yes? No? Maybe so?
What are you supposed to do? What are you supposed to set the Y to do?
Well, you can still, you solved for x. The x's are 0 to 4.
Yeah.
But we need the y, so when you plug 4 in, your y value is 16. When you plug 4 in for x,
Yeah.
what do you get for y?
We get this more from.
You just told me 0 to 4.
Yes.
And that is for the x's.
Yeah.
But we need the y's.
So all I do is plug it in.
Yes.
So if I plug 0 in, you got 0, that's.
Okay. Now, before we get too excited, let's go ahead and rewrite our equations. This line we need to be x equals y over 4. And this parabola we need x equals positive radical y since we have the positive piece. Okay? So, when we go to do this integral, we have 2 pi times radius times height times our thickness is now dy. Okay? Here's where it changes. How far away are any of these rectangles from the x-axis? They are y away. Times how long are each of our rectangles? In this case, now we have to do right minus left. So on the right, we have radical y minus on the left, y over 4. Okay? Just to save us a couple minutes, go ahead and do this one by hand, or go ahead and do this one with your calculator. What do we get? 21 point what?
8,171. 24.7. Not bad.
Okay, Sammy, what'd you get?
428.932.
Jeez.
Jake, is this what you got?
Yes.
You put it in your calculator. That's what you got. Okay. All right, go ahead and get your gold sheets out. I'm going to pick a few of them that I do want you to do by hand. Now, if we were to do these by hand, what would be the first step?
Graph, draw picture.
Okay, how about this? Once we get the integral set up, and I said integrate by hand, what would you have to do first? You would have to distribute y through and then take the antiderivative. Okay? So, you have your gold sheets out? These are the ones I want you to do by hand. 1, 3, 7, and 15. 1, 3, 7, and 15. I know 1 is not underlined, but it's a good by hand problem. What I'd like you to do, because we have 5 minutes left in class, I want you to set up and complete, if you can, one of those problems. It's March 1st. Happy March 1st.
March 1st, Iowa State's still in 2014.
They will be for 6 more days, buddy.
Especially after that one.